My name is Christopher Yamamoto, and this is my Physics Lab 5 presentation. For Lab 5, I decided to observe the motion of an object falling off the edge of a platform with an initial negative horizontal velocity. The motion of the object came from a video I recorded myself. Once I captured the object, I analyzed its motion and compared it to a computational model that matched the object's motion. To analyze the video, tracker was used to extract the object's position at corresponding times, and to create the computational model, GlowScript was used to code a theoretical version of the object's motion. The result of the lab showed that you can create a similar but not perfect simulation of a real-life event by inputting the forces acting on the object. Models and fundamental principles. Newton's first law of motion states that an object at rest remains at rest, and an object in motion will remain in motion unless acted on by a force. In this lab, the object will follow this law as the object retains its horizontal motion throughout the video. Newton's second law of motion states that the force acting on an object is equal to the mass of that object multiplied by its acceleration. In this lab, the motion of the object is dependent on the forces acting on the system and the mass of the object. The physics ideas used in this lab include inertia, velocity, net force, position, displacement, and acceleration. A tennis ball was used as the object of the motion. The tennis ball was rolled off a table given an initial velocity in the negative x direction. A ruler stick was included in the frame in order to calibrate the motion with a specific distance when analyzing the video and tracker. The tennis ball was to drop off the table to track its motion as it fell and hit the ground. This was the video captured. This video was then put into Tracker, and using Tracker's tools, I was able to record the object's position every few frames to chart this data and create these three graphs. These graphs represent the object's x and y positions and the object's somewhat instantaneous velocity in the x direction. In order to make the computational model, some assumptions had to be made. One assumption was that there's no friction, wind, or an uneven surface angle that was computed into the code. I assumed that there was no speed in the y direction at the start of the motion, and the initial horizontal velocity used for the computational model was the average horizontal velocity of the object captured in the video. The code on the right shows the initial conditions from the system that were put into the code. It includes the tennis ball's mass, its initial position, initial velocity, and the magnitude of the force of gravity. The picture on the right shows the code that was used to predict the motion of the ball over the time period that it was falling. It updates the velocity and position of the ball under the effect of gravity using the position update and velocity update formulas. After running the code, these three graphs were created, showing the x position over time, the y position over time, and the y velocity over time. So, once the real-life tracker motion and computational motion were completed, I put the data into Excel to create these four graphs. The two blue graphs on the left represent the x and y position over time for the real-life motion, and the two graphs on the right show the predicted motion of the ball from the computational model. To compare the two motions, I combined the motions of the object to see the difference. As seen in the graphs, the tracked motion in blue and predicted motion in red do not match up perfectly. The tracked motion is a little lower than the predicted motion, likely due to drag. However, both graphs end in nearly the same place. As seen in the previous slide, the motion was not perfect, so here are some possible sources of error. The camera was not set up on a stand, and there is some camera distortion from the angle it was recorded at. The drag force was not added into the calculation, which affected the motion of the ball in the real world, and the setting was not an ideal perfect setting. What does it mean? The results of this experiment tell me one main idea. This idea is that the motion of an observed object is not as perfect as the motion of a predicted computational model of the object. However, the computational model can display the motion of an object to a close but inaccurate degree. As seen on the graphs, there is a close resemblance. In conclusion, using computational models in imperfect environments will likely not give an exact replica of the motion in the real world, but if a rough estimate is needed, a correct computational model can be used. What if I used a bowling ball instead of a tennis ball? If the tennis ball in the experiment was replaced with a bowling ball, the mass of the object would be much higher, which would cause the gravitational force acting on the ball to be much higher. However, the mass of the object does not affect the motion of the ball. This means that the bowling ball and the tennis ball will fall at the same rate in this situation, resulting in the same y position graph.